Okay, so I want to start by saying thank you for the Fusion Report Forum for organizing this webinar and discussion. I think it is very timely and important, and happy to be able to contribute to it. And before we start, and for those who I have not had the pleasure of meeting, my name is Oded Gour-Lavie, a retired Rear Admiral from the Israeli Navy, and the CEO and co-founder of nT-Tao. Our talk today is about Fusion 2035, the 10-year shot clock. Before I continue, I would like to give you a little bit about myself, a little background, and then we'll dive right in. And as you can see on the picture, I'm the guy on the left, standing behind me, one of the submarines. Many years underwater, leading teams, critical missions in times of high uncertainty, that required careful planning and even stronger execution. The reasons that I stayed in the IDF for 30 years was about securing the future for my children and their children. And that is the same why that I bring to this mission here on Fusion. My passion for energy started as a young submarine captain, where I had a kind of a personal connection to every electron running through the submarine. It was literally a life and death situation. Later in my career, while at Harvard, researching the relationship between global security and energy, it was clear to me that would be the biggest challenge moving forward. Energy creates everything from water to AI. And what we need as humanity is to secure abundant energy on a global scale. I started nT-Tao back in 2019 while at MIT Sloan on a new mission to harness the super innovative thinking of Israel tech to the fusion sector, standing on the shoulders of 80 years of experience and experts and knowledge, and bringing that forward to reality. Our talk today, again, is about Fusion 2035, the 10-year shot clock. There are a few challenges and opportunities that we will discuss. But before we get there, I want to briefly present nT-Tao's approach to fusion, which is a compact system, and the way we plan to beat the clock and how we do it cost effectively. So let's dive in. So nT-Tao, we're building a compact system of a 20 megawatt power supply. We believe it's going to be fast go-to-market, easy, quick maintenance, relatively easy, even for a full core replacement, easy deployment, scalable. It can connect to the grid, can be scaled to a bigger plant for the grid in a modular fashion, but can also be on a microgrid and definitely or totally off-grid. It is optimized for that kind of distributable, scalable power, which is the power ecosystem we're heading towards. We can see it mainly due to renewables that are creating the necessity for the power grid to go distributed and be more able to work in distributed modes. But also, and for a stronger reason, we need that distribution for security and redundancy, for national security and redundancy, which are very, very important. What is our differentiation, or where are we situated? This partial map has been developed over several decades. And following extensive research into the most efficient areas for fusion work, our focus has been on high energy systems driven by the need for strong power supplies, pulse power, and high density plasma. We sought the most optimized and efficient regime for fusion, which led us to recognize the need for the high density conditions. At this density, we saw an opportunity to combine the magnetic confinement technologies with the most advanced and mature heating and energy transfer systems. Those are the pulse systems on the left side. And on the right side are the magnetically confined plasma, the tokamaks, the stellarators. This combination of pulse modes and the magnetic confinement as shown in this figure, is the most efficient approach, we believe, that is enabling a compact fusion system and actually lends itself to a smaller compact system. And so we went for this optimization for high density, higher efficiency, and the combination of the two. The figure illustrates the opportunity that we are seeking, and we believe it is the right approach. So the solution that we are building, as we said, is using the backbone of the magnetic confinement based on the stellarator design, fast heating by very, very strong pulse power and power electronic units, and active stabilization fields. All of those combined enable to be performed on this system. In the picture, what you can see is our current system on testing and experiments, C2A. That is the third system of that sort and model, and it incorporates the design and the heating and preheating systems that we have built. Over 1,600 pulses already being pulsed on this system, and creates a huge amount of data points for our next design. This solution, as we say, is incorporating all the parts together, and the engineering milestone that led us to this stage is a very rapid full prototype engineering cycle, from simulation to design to engineering, building, and eventually testing each and every part of the system as components and eventually connecting them all together. The validated C2A backbone of stellarator has been tested at the end of last year, and we're continuing and progressing very quickly to the next stages. The power that you can see here, those power units, those are proprietary power units that we've built in order to be able to push those magnets and to heat the plasma all together with the entire system and machines. The simulations that have been enabling us to design as part of the full prototype engineering cycle are based on simulation codes from Princeton, the desk one, the Strufi with the MHD from Max Planck, and other MHD and gyrokinetic kind of simulations and more. Those are all incorporated in the process of design. We're adding top-notch diagnostics that we've built in collaboration with the top institutes in Israel and abroad. And those are all incorporated in order to really get all the information through those experiments that we're doing. And we also are building HTS magnets that are specifically designed to be able to work in very high pulses. So those HTS magnets will be tested. They're already built and will be tested in a pulsed environment very, very soon. So let's go now, after looking at nT-Tao and our approach and general approach, and a little bit about technology, let's go and talk about the bottlenecks and what will take us to 2035. The bottlenecks, the main bottlenecks, I divide to three main vectors: the reactor challenges, the full system challenges, and the market and public challenges. And if we take a look at the reactor challenges, we all have the goal of Q greater than 1, and on the engineering side, not the scientific side. And that's a big goal for everyone to achieve, for us as well, obviously. The next stage, and that's a big issue, is reactor to electricity path. And that's something that part of it can be in collaboration, and part of it is internal to each company. Some companies have their own special means of moving from fusion power to electricity. I believe that will be discussed as well by others. But we're taking the path of the more conventional, moving through steam or other means to run a turbine and then a generator. Tritium breeding technology, that's an essential challenge that everyone using deuterium tritium needs to resolve. Deuterium tritium is the easiest kind of fusion fuel in terms of temperature and energy, but also has the lack of tritium. So tritium breeding is essential, and that's an area for a lot of collaboration possibility in the ecosystem. Trained workforce, that's essential. And that's a big issue for this decade. And when we increase space, increase the capability of the companies in order to move faster, but also achieve our goals for 2035, we need a trained workforce. And that's another challenge that we have in front of us. Another one, and the discussion on full system challenges. And that is, first of all, government investment to reduce supply chain constraints. When we discussed specific supply chains, and that can be maybe in another discussion, but government can signal suppliers that they can reduce their risk and join the ecosystem and start pushing forward in order to be ready for 2035. Some of that is mass production and distribution, especially for a compact system like we are planning. Mass production is the way, which will also reduce the cost, but is also something that we need to be prepared for. So that's another challenge that we see ahead. And materials and manufacturing, that in precision manufacturing and certain materials that need to be created or developed for the plasma-facing materials, etc., and other elements in the machines, that's also an area for collaboration. And a lot of that can be done and reduce risk mutually. And then the last one bottleneck that we want to discuss is market and public challenges. First of all, more private and public investment is required for the R&D phase, but also for the reduced process of going into market and creating the first of a kind, etc. So that's part of the challenge for the public. Regulatory policy that enables us to move faster in the process of the development, but definitely to be prepared for the final market process. International regulation is also, we see some of that being created already in the IAEA, but I think we saw the NRC leading in the US in terms of regulation for fusion, making the differentiation between fission and fusion, etc. That's a very important thing, and we should see that going on a global scale as well. And regarding public awareness, that's not a small thing as well. In terms of the community preparedness, media is part of the process, and education. We are very much engaged with students and teenage high school students to come visit, learn what is fusion, get aware of where we're going, and be the next generation. Decade from now, they will be leading this process in the market and creating the new generation of fusion reactors as well. So those are the main bottlenecks that we see ahead of us. So moving on to the global leadership challenges, because most of challenges and even bottlenecks, eventually we need leadership to lead and solve. And the race is on a global scale. So what we see the need for stronger government leadership to reduce supply chain risk. We discussed that. And that's leadership, not only the process. And then common challenges are common risk. And that's an area for collaboration opportunity. We had a few challenges. One of them is the tritium breeding, the blankets that are out there, the plasma-facing materials, and other issues that are all surrounding those reactors and systems. Those are excellent areas for collaboration. I mean, if submarines and submarine forces from around the globe can collaborate on safety and rescue for submariners within submarines, while all their missions are always super secret, but on those aspects, we can collaborate, and we do on a global scale. I think we definitely can find a way to make more collaboration in the fusion ecosystem in the same manner. Also, multiple shots on target are essential. And I think the fact that we have about 50 startups, different technologies, and the more different technologies that we are pushing at, the more chance we have to get by 2035 with a full fusion capability going to market. So this is very good and very important. For that, we need the leadership in terms of the funding, the government as well for that, and also to create national strategies that can push forward into that process. And enabling regulatory framework internationally and nationally, I think a very important aspect of that. We see, as I said, the NRC moving forward. We see other countries pushing as well and getting to that stage. And what I think is an important proposal that we suggest is to propose a US-led sandbox for sub 50 megawatt fusion systems, enabling fast-track approvals and global alignment. It's a proposal that the goal is to de-risk both the technology and the regulatory process at the same time, so that when 2035 arrives, fusion isn't stuck in licensing purgatory. Key features of fusion regulatory sandbox could include, for example, eligibility limits, i.e. like only systems under 50 megawatts with specific safety case parameters, streamlined approvals, meaning shorter timelines for siting, environmental review, and operational permits, and standardized safety cases, shared technical baselines for shielding, tritium handling, and operational limits, and international reciprocity. Data from one sandbox nation could be accepted by others to speed global rollout. So we believe that that's an opportunity here as well. And for a summary, and just to summarize everything, compact, we believe and think that compact is the right path. We understand the technological hurdles, but also the capabilities that enable what we want to achieve. We're quickly reducing those risks. And to get to 2035, we will need more collaboration than we see today. To get to 2035 with the market ready requires more government involvement. Fusion by 2035 isn't a hope, it's our mission. And as I used to say to my sailors, it's all hands on deck. The race is on. Thank you.